Hello, welcome to Marine Gurukul video series. We are pleased to present this video in which we shall discuss some of the terms that are related to the ship form. In this video, we shall try and understand, illustrate and define the following: camber, rise of flow, tumble home, flare, shear, rake, parallel middle body, entrance and the run. Camber is the curvature of the ship's deck in the transverse direction. That is, curvature of the ship's deck from center line and downwards to the sides. What we are seeing on the screen is the transverse section of a ship coming up with the ship side, keel, and now the deck. Now, if you have the center line of the vessel, now camber is measured between the deck height at the center line, that means here, and the deck height on the sides. That means if we draw a tangent to the deck at the center line and we draw another line where the deck edge meets the ship side, the difference between these two, you can see in the diagram, is the measure of the camber of the deck in this particular case. What is the purpose of camber? Camber facilitates water freeing on the exposed decks. That means when the water on the deck comes, either the rainwater or when the seas are shipped on deck, the camber, the slope of the deck, facilitates the drainage of the water or the water freeing from the decks. So that is the purpose of camber on the decks. Rise of floor is the upward curvature of the keel from center line to the sides. If it's provided, then that is called as rise of floor. What we see is the transverse section of the ship coming up on the screen with the ship center line marked. Now, the level of the keel at the center line is here. If there is a difference in this level with respect to the level of the keel where the turn of bilge starts, then that change in level is called as the rise of floor. So we draw a tangent to the keel at the center line, then we draw another line where the turn of bilge starts, and this difference in the level of the keel is what is called as the rise of floor. Now this rise of floor, if provided, is to facilitate the drainage of the liquid in the DB tanks to the pump suction. Rise of floor, if provided, is usually of a small value because it is just to facilitate drainage of the liquid to the suction. Tumble home. Now in some ships we may find that the side shell plating, as it comes closer to the upper deck, may be curved slightly inwards. If there is a slight inward curve of the side shell plating as it comes closer to the deck plating, that is what is called as the tumble home. So in some ships, the midship side shell in the region of the upper deck is slightly curved towards the center line, narrowing the midship side shell. This narrowing of the side shell is what is called as the tumble home. You can see again the midship section of the ship coming with the center line marked. And what we see here is that the side shell, when it meets the deck edge, it's here. But if the side shell was to go straight as it was coming up from the keel, then that would have been here. What we see that this upper part of the side shell is curved inwards, and this measure is what is called as the tumble home. Whereas camber and rise of floor had a purpose, tumble home has no technical advantage. It may have been introduced just to maybe give a better look to the ship, better appearance. The modern day ships, we hardly get to see this tumble home. Anyway, as a term, tumble home is the inward curvature of the side shell as it comes up to the deck. Flare is the outward curvature of the ship's hull plating with increasing height. As the ship's side shell comes up from keel to deck, if it has an outward curvature, that is what is called as the flare. We can see the bow of this ship in the picture. If we just follow this plating at a certain frame and come up, we will be able to appreciate this outward curvature of the bow plating. And these two red lines will help us in appreciating the outward curvature of the bow plating. And this is what is called as the flare. Now, if we have to draw a separate diagram, we can draw it like this, with the blue line showing the deck and the keel. We have the center line of the vessel, and this outward curvature of the side shell is what is called as the flare. Now the flare can be at the bow, could be at the stern, but the flare at the bow, which is called as the bow flare, is of special importance as it has certain distinct advantages. Number one, flare anywhere, and so the bow flare increases the deck area. So in case of bow flare, the deck area of the forecastle deck is increased, which gives us sufficient room for mounting of the mooring equipment. The flare at the bow also helps in providing a clear lowering area for the anchor, thus reducing the risk of the hull damage by the anchor. You can see in this picture, if this anchor is lowered, because of the flare, the anchor is going to be lowered clear of the ship's hull. Flare improves the stability by providing increased reserve buoyancy. Why? Because of this outward curvature, as we are coming towards the deck, the enclosed volume increases, hence increasing the reserve buoyancy. The bow flare provides increased buoyancy at the bow, thus providing more resistance against nose diving. So provides increased buoyancy when pitching, controlling immersion of the bow during nose diving of the vessel in the trough. The bow flare also helps in driving away water when the ship is in light or calm seas. However, flare, excessive flare may not be desirous. The modern container ships, which have excessive flare to accommodate more containers on deck, are also facing the problem of parametric rolling and excessive torsional stresses. So on one side, flare has advantages. On the other side, excessive flare could result into parametric rolling as well as excessive torsional stresses. Shear. We learned a while back about camber being the curvature of the upper deck or the exposed deck in the transverse direction from center line towards the side. The upper deck has a curvature in the longitudinal direction, in the fore and aft direction. That is what is called as the shear. So shear is the curvature of the deck in the longitudinal direction, with deck rising from midships towards the ends, that is the forward end and the after end. We can see this picture. In this we can see the upper deck rising from midship towards the forward end and also towards the after end. This curvature is what is called as the shear. Now this shear is measured at the perpendicular. So we have the water line of the ship coming up, then we have the forward perpendicular, we have the after perpendicular. Now to measure the shear, we draw a tangent to this curve of the deck. So we draw a tangent. Now this tangent is drawn to the curvature of the deck, and we read off the difference here at the perpendiculars, and we say this is the shear shown in red, this is the shear forward, and likewise we have the shear aft. The shear forward is usually more than the shear aft, as also evident from this diagram. Shear on the exposed decks reduces the quantity of shipped seas. Why? Because the ends have been raised, thus helping in reducing its impact on the ship stability. Shear increases the volume of reserve buoyancy at the ends because the level has gone up, so that will increase the reserve buoyancy at both the ends. Acceptable shear also entitles a ship reduction in freeboard under the load line convention, which you may be able to appreciate once you go to higher grades and learn about assignment of freeboard. Shear forward may also be used to ensure that the vessel has minimum bow height as required under the load line convention, because under the load line convention every ship will have to have a certain minimum bow height, and shear could be one way of vessel attaining the required minimum bow height. Rake is the inclination of the keel with respect to horizontal, or the inclination of the ship's stem with respect to vertical. Accordingly, the rake can be classified as stem rake, also called as the rake of the stem, and keel rake, also referred to as rake of the keel. When the term only rake is used, it is assumed to be stem rake or the rake of the stem. Rake of the keel is the inclination of the keel in the longitudinal or the fore and aft direction with respect to the horizontal. How do we measure it? It's the measure of the rise or dip of the keel from after perpendicular to forward perpendicular. Trawlers and tugs usually may have keels raked aft. Why? Because you want more depth aft to accommodate maybe a proportionately larger diameter propeller, and such keels will be referred to as aft raked or raked aft. We can see this diagram coming up here where we are drawing the outer boundaries of the ship in a profile view, and we can see this keel is not parallel to the deck. We have more depth of the keel aft compared to the depth forward, and this is what is called as keel raked aft. And how do we measure the rake? We draw this horizontal at the level of the keel in the after part, and we measure this height difference of the keel at the forward perpendicular, and that is what is called as the keel rake in this particular case. There may be vessels with forward rake of the keel that may facilitate bringing propellers above the keel line. That means there the keel at the forward end would be dipping down, and that will be called as keel with forward rake. In modern flat bottomed ships, the rake of the keel may be observed at the forward end only over maybe 20 to 30 or 20-25% of the ship's length, as shown in this diagram which is coming up. You can see here the modern ships may have a rake like this. You may have seen the bulbous bow. If you have seen the ship in the dry dock, you may have found that the center line blocks end at a certain stage, and after that the bow lifts up. That is because of the rake of the ship in the forward part. In such a case, this will be the measure of the keel rake. Rake of the stem. Before we talk of the rake of the stem, let's understand what is stem. Stem is the bow frame, the forwardmost bow frame right at the forward end, where the side plating from both sides comes and gets connected. So it is right at the forward end of the ship. We can see this profile view of the ship coming here, and this is the water line, and this one here out here is the stem of the ship. At its lower end, the stem is rigidly connected to the ship's keel to provide continuity of the strength. The stem could be a heavy flat bar stem or could be a rounded plate stem. In today's big merchant ships, it's usually a rounded plate stem. Stem rake or the rake of the stem is the measure of the inclination of this stem with respect to the vertical. So to measure the stem, let's draw vertical to the water line. This angle here that the stem is making with the vertical is the measure of the stem rake in this particular case. Stem that is perpendicular to the water line, that means has a zero rake, is also referred to as a plumb stem. Stem with a rake, as in this case in this drawing, is called as a raked stem. So you may have a raked stem where you'll have some rake, or you may have a plumb stem where the rake would be zero. Let's now discuss three terms: parallel middle body, entrance, and run. Here we have a picture of a ship. Let's visualize the cross-sectional areas of the ship at different stations along its length. Let's visualize at station 1, station 2, station 3, and station 4. What do we mean by the cross-sectional area? At the designated station, we cut the vessel from one side to the other and have an end on view, and the cross-sectional area from keel to deck would be the cross-sectional area at that particular station. I'm sure looking at the picture, all of us would agree that the cross-sectional areas at all these four stations, 1 to 4, are going to be different from one another. Let's carry out the similar exercise at the after end at station 5, station 6, and station 7. Again, looking at the hull form in this region, I'm sure all of us would agree that the cross-sectional area at each of these stations is going to be different. Now look at the hull form over this length from station 4 to station 7. I'm sure you'll agree that if we visualize or we get the cross-sectional area at any point over this length, the cross-sectional areas would be identical to one another. This length of the ship over which the cross-sectional area remains constant in shape and size is called as the parallel middle body. So parallel middle body is the length of the ship over which the cross-sectional area of the ship remains constant in shape and size. Now this length of the ship forward of the parallel middle body in the bow region, where the cross-sectional area was changing from stem to this place, station number 4, is what is called as the entrance. Why? Because it is this part which cuts through the water, and it's like as if it's entering the water. So this is what is called as the entrance. So entrance is the immersed body. Now here, please remember, entrance is the immersed part of the hull of the vessel forward of the parallel middle body. So immersed part over this length is called as the entrance. And likewise, the part aft of it, which is running behind, is called as the run. So this part, immersed part of the hull over this length, is called as the run. Run is the immersed body of the vessel aft of the parallel middle body. So we have the parallel middle body, we have entrance, and we have run. Let us also learn to draw the diagram in which we can show these three terms: parallel middle body, entrance, and the run. One diagram that can be used is the plan view. You can see the plan view of the ship coming up here on the screen. We have the center line of the ship here, and now we see that over this length of the ship here, the cross-sectional areas would be identical in shape and size. So this length represents the parallel middle body. The immersed length forward of it would represent the entrance, and the immersed body aft of it, the length will represent the run here. Same thing can be represented in another diagram, which is a graph of the cross-sectional areas of the ship drawn at different stations along its length. For same, we have on the x-axis the length of the ship, the middle part of the line representing the midships. One side we have the forward end, on the other side we have the after end, and we have the y-axis on which we have the cross-sectional areas, and these cross-sectional areas are in the units of fraction of the cross-sectional area in the middle body, parallel middle body or midships. So we can take the cross-sectional area midships as 1, and other cross-sectional areas can be fraction of that. And then if we plot them, then we get this as the cross-sectional areas in the forward part, and then we have in the middle body the cross-sectional area being 1, and then in the after part. Now you see, you can correlate this graph with this diagram. Right at the bow, the cross-sectional area is nearly zero. It keeps increasing as we keep going aft. Then in the middle body, the cross-sectional area remains the same. And then in the after part, it decreases and again becomes nearly zero. So this green graph here is the graph of the cross-sectional area at different points along the length of the ship. And what do we see? That in this case, from this point here to this point over this length, the cross-sectional areas have remained same, and length over which the cross-sectional areas remain same in size and shape is called as the parallel middle body. The immersed body forward of it would be the entrance, and the immersed body aft of it would be the run. So we could use either of these two diagrams or maybe both of these depending on how much time you have to complete the question. Now, what is the importance of these three terms? Why are we studying them? The form of the entrance and the parallel middle body will have a direct effect on the hull resistance as the ship tries to cut through the water. And that hull resistance will have a direct bearing on the fuel efficiency. So therefore, form of the entrance and middle body have a direct bearing on the fuel efficiency of the vessel. Likewise, the parallel middle body and the form of the stern, that is the run, will have a bearing on the wake formation as the ship moves through. And this wake formation again has an effect on the propulsion efficiency or indirectly on the fuel efficiency. It will translate into fuel efficiency. So therefore, these three terms, or the form of the entrance, the middle body, and the form of the run, will have a direct bearing on the fuel efficiency of the vessel, and that is why we are trying to study them. We come to end of this video. We hope you like this video and it's useful to you. Please do subscribe to the channel if not already done. Feel free to share your feedback through comments or through email. Write to us on marinegurukul@gmail.com. Thank you very much for watching Marine Gurukul video series. All the best.